So this is a real t-shirt that I found online. If you want to own your own calculus pun t-shirt, you too can go and search on your favorite online shopping retailer and get your own 10-line t-shirt. So this is our first lesson in Chapter 8, Applications of Differentiation, and we're going to be looking at finding equations of tangent and normal lines. This lesson covers some content that you would have learned in Methods Unit 1 and 2, but we may be looking at some slightly more complicated functions. So we're going to be looking at how we calculate the gradient at any point on a curve, and then we're going to go into finding the equation of a tangent line and the equation of a normal line. So a tangent line is a line that just touches a curve at one particular point. So you can see that we've got our red function, f of x, and then that blue line there is what we would call the tangent line, okay? So the slope or the gradient of the tangent line is the derivative at that point, okay? So you can see on the curve there that the slope of a tangent line, it would change at any point on the curve. So for example, if I drew a tangent line, let's say here, I drew another tangent, so that's a tangent at that point. This gradient of this line would be different to the gradient of the line, the blue line that's on there, okay? So we need to use differentiation to be able to calculate the derivative at any particular point on a curve. So we'll take a look at how we do that with this example here. So first of all, we're going to calculate what we call the gradient function of our curve. And the gradient function is just the derivative, okay? So these two things mean exactly the same. Okay, so when we want to calculate the gradient function, we just calculate the derivative. So I'm going to write that as f dash x. That's going to be equal to, I'll do 3 times 2 is 6x squared plus 2, okay? And if you need to go back over how to calculate derivatives, that's all in Chapter 7, okay? The next step we're going to do is to find the gradient of the tangent at a particular point. So we want to know what is the gradient at the point where x is equal to 1. And to do this, all we have to do is substitute x equals 1 into the gradient function. So we're going to substitute f dash 1. So wherever I see an x in my gradient function, I'm just going to replace it with a 1. So I'm going to do 6 times 1 squared plus 2, and then work out that answer. 6 times 1 squared is 6, plus 2 would be 8. Okay, so the gradient of this curve here at the point x equals 1 is 8. So we can find the gradient of a function at any point really easily using our CAS calculator. So the first thing we'll do is we'll go into the menu. And we want to go into the calculus menu, which is number 4. And then if you select number 2, you'll see its derivative at a point. Okay, so the variable we'll use is x. We don't need to change that. The value, what you put in for the value is the x coordinate. So in this case, we're asked to find the gradient of the graph at x is equal to -1. So we're going to input -1. And we want to calculate the first derivative, so we're not going to change that there. Press OK. Now what you've got to do is just in that box is you're going to put the function in. Okay, so for this one, we're going to put in the square root of x plus 3. Okay, and then we will just press enter, and our answer here is √2 on 4. And we always want to give an exact answer to our questions on the calculator paper, unless it asks you for a particular number of decimal places. Okay, but for this question here, the answer √2 on 4 would be perfectly acceptable. So now we're going to move on to finding the whole equation of the tangent line. So in the last section, we were just looking at calculating the gradient. Now we want to go on to finding the whole equation of the line. So you should know that the equation of any line is just y minus some point, y1, which is equal to the gradient, which we normally represent with the variable m, times x times x minus our x coordinate of our point, okay? Now, that looks very, very similar to the equation we've written in the purple box above. The only difference is this here, but you can see that Remember, the derivative at that point, that is actually the gradient, okay? So those two equations are exactly the same, okay? So I've written some steps for you here to find the equation of the tangent line. The first thing that you'll do is find the gradient, okay, by calculating the derivative at the given point. If you need to, you'll have to find the y-coordinate of that given point if it hasn't been given to you in the question. And then you'll use the equation of a line formula to find the equation of that particular tangent line. Okay, let's look at an example of how to do this. So we want to find the equation of the tangent line to the curve f of x, which is equal to the square root of 2x plus 1 at the point x equals 4. So remember, our first step is to find the derivative at that point. So I'm going to start by rewriting f of x as 2x plus 1 to the power of a half. Okay, because that's going to help me to find the derivative. And here I've got to use the chain rule. So the derivative of f would be 1/2 2x plus 1 to the power of negative a half. And that's going to be times the derivative of what's inside those brackets, so times 2. Okay, very nicely here. A half times 2 is just 1, so those cancel out. And what I'm left with is 2x plus 1 to the power of negative a half. Okay, now I've got to find the value of the derivative at the point that I've been given. So at x equals 4. So I'll substitute x equals 4 into my derivative. Okay, so 2 times 4 is 8, plus 1 is 9. So I get 9 to the power of negative 1/2. Negative 1/2, I can rewrite that as 1 over the square root of 9. Okay, the square root of 9 is 3, so I end up with 1/3 as my gradient. Okay, so I'm going to just write in here that variable m to show that I've calculated the gradient at the point x equals 4. The next thing I'm going to have to do is find the y-coordinate, and I'm going to find the y-coordinate by substituting my x equals 4 into my original function. Okay, this is really important. You're substituting back into the original function to find your y-coordinate, okay, not the derivative. Okay, so I'll just write down the step, find the y-coordinate. Okay, so f at 4 is the square root of 2 times 4 plus 1, which is the square root of 9, so 3. Okay, so the coordinates I'm talking about, or the point I'm talking about, is the point 4, 3. X equals 4 and y equals 3. So now I'm going to take the point 4, 3 and my gradient 1/3, and I'm going to find the equation of the line. So y minus y1 would be y minus 3. That's going to be equal to the gradient times x minus 4. Okay, so I'm first going to expand that bracket there. Y minus 3 is equal to 1/3 x minus 4/3. And then I'm going to add 3 to both sides. Y equals 1/3 x minus 4/3 plus 3. Okay, adding those two coefficients together, I get y equals 1/3 x minus 4/3 plus 3. That would be plus 9 over 3 would give us 5/3 there. Okay, and so often you're asked to answer in terms of y equals mx plus c. So there's our final equation of the line. Again, our CAS is going to be really, really helpful here. If we're on a tech-enabled paper, we can just use our CAS calculator to find the equation of the tangent line. So we're going to look at that same example that we just did, but we're going to see how quick and easy it is to do on our calculators. So again, we're going to go into our menu, our calculus menu, so number 4, and then we're going to go all the way down to number 9, which says tangent line. Okay, so in those brackets there, what you've got to do is first enter the equation of the function that we're talking about. So what we would enter here is the square root of 2x plus 1. Okay, and then we're going to put in a comma. And then we're going to put in the x coordinate, and we're going to write it as x equals 4 in this case here. So just going to write in x equals 4, and then we'll press enter. And you can see here we get the equation of the tangent line. It looks a little bit different. You won't get the y equals, but you can see that x on 3 or 1/3 x plus 5/3. Okay, so really nice and simple. That's how you'd find the equation of the tangent line using your CAS. So in this last section, we're going to have a look at the equation of the normal line. So what a normal line is it's just a line that is perpendicular to the tangent line. Now, sometimes VCAT doesn't use the terminology normal anymore, but they can still ask you to find the equation of a line that is perpendicular to the tangent line. So what you've got to remember here is that if you're looking at two gradients of lines that are perpendicular to each other, okay, when you multiply them together, so I'll write this out, the gradient of the tangent times the gradient of the normal line should equal -1, okay? The way I like to think about this is that the gradient of the normal line is the negative reciprocal of the gradient of the tangent line. So with numbers, if like the gradient of the tangent was equal to, say, 3, then that means the gradient of the normal line would be -1/3. Okay, so that's all that means. So there you'll see that the equation of the normal line is very similar to the equation of the tangent line. It's just that our gradient now is -1 over the derivative at whatever point we're looking at. So the steps that you want to follow to find the equation of the normal line are very similar. We just have to do one extra thing, which is like step 2 here, okay? So we still have to find the gradient of the tangent first, okay? We find the derivative, and then we substitute the point in that we're given. Then you've got to find the gradient of the normal by taking the negative reciprocal of the gradient of the tangent, okay? Then you're going to find the y-coordinate, like normal, or like usual. I shouldn't say the word normal again. And then you'll find the equation of the normal line using our equation of the line formula. All right, let's look at an example to see how we would do this. So we're going to do this worked example first by hand, and then I'll show you the steps to take on the calculator to do this really quickly. Okay, find the equation of the normal line to the graph f of x is equal to log of 2x base e at the point 1/2, 0. All right, so we need to remember that to calculate the derivative of log base e, it's just 1 over 2x, okay, times, so we're using the chain rule now here, times the derivative of whatever's inside those brackets. So the derivative of 2x is 2. Those cancel out to just give us 1 over x, okay? Now, I've got to still substitute in the point x equals 1/2, okay? So f dash at 1/2 is equal to, okay, 1 over 1/2, which is 2. So that's the gradient of the tangent, okay? I'll just write that in. The gradient of the tangent is 2, but I want the gradient of the normal line, okay? So the gradient of the normal line is the negative reciprocal of 2, which is -1/2, all right? My next step now is to find the y-coordinate at the point x equals 1/2, okay? So y would be equal to log base e of 2 times 1/2, which is 1, okay? Now, log of 1 base e is just 0. All right, because e to the power of 0 equals 1. So we get y equals 0. Oh, and that was actually given to us in the question. So I've done a little bit more work there than I had to, but there you go. Just remember to calculate the y coordinate. That's given to us in this one here. Now I can go on and find the equation of the line. So I'll just do it in a different color to sort of keep things a bit clear. But I'm going to go over here. Y minus y1 is equal to, now I need the gradient of the normal, x minus x1. Okay, so y minus 0 is equal to -1/2 x minus 1/2. Okay, and if I wanted to simplify that a little bit, I could just write it as y is equal to -1/2 x plus 1/4. Okay, so now let's compare that to what we get using our CAS calculator. So to do this on our CAS, all we're going to do is we're going to go into menu, we're going to go into calculus, and then we're going to go down to the bottom where it says A, normal line. So I'm going to choose option A, and that's going to give me the equation of the normal line. So now I need to put in for my function log of 2x base e. And then I'm going to put in the point, which is a half. So we can put in that as a fraction. And pressing enter there, I get 1/4 minus x over 2, which is exactly the same thing. It's just the two terms are written in a different order. It's the same thing as -1/2 x plus 1/4. Okay? Okay, so that wraps up our first lesson in our applications of differentiation unit. Remember that the derivative and the gradient function, those two things mean exactly the same thing, okay? So the derivative at a particular point, that gives us the gradient of a tangent at that point, and then you've got your two equations there, equation of a tangent line and equation of a normal line, okay? In the next session, we're going to have a look at another application of derivatives, which is rates of change. To introduce this topic, I've got a link for you, which is the women's 100-meter freestyle swimming finals from the 2020 Tokyo Olympics. Now, you can start this video just at like about 3 minutes. That's when the race starts, and it just takes about a minute to watch, okay? You don't have to watch the entire sort of video that's linked there. So just the actual race itself. And while you're watching it, I want you to just take note of the speed of the swimmers and what happens to their speed throughout the race. Okay, so I hope you enjoyed watching that sort of rerun of the 2020 Olympics. The Aussies do really, really well in that race. And that's just to introduce our topic, which is rates of change. So if you recall from Methods Unit 1-2, a rate of change is just how one quantity changes with respect to another, and speed is a very typical rate of change that we talk about a lot. Now, in that swimming video, they start to show you the speeds about 25 meters, I think, from the end of the race. And so you can see that the swimmer's speed actually slows down a little bit. So they're probably at their peak speed near the end of the race, and then they sort of slow down a little bit as they finish. Overall, though, they also have what we call an average speed, and that's just looking at their total distance divided by their total time. So for that race, that was a 100-meter swim, and it took 51.96 seconds. So to work out the swimmer's average speed, and that was the gold medal winner, you would do 100 meters divided by 51.96 seconds, which gives us an average speed of 1.92 meters per second, which is pretty different from the speeds that we saw sort of on that video, which were more like 1.7-ish meters per second. So that's just kind of contrasting what we mean by average and instantaneous rate of change. The instantaneous rate of change would be that one that was changing throughout the race at different times. So again, what we're going to look at is our two different rates of change. We're looking at average rate of change first in this video, and then we're going to look at instantaneous rate of change, which is where our calculus comes into play. Okay, so a rate of change just is a measure of how one quantity changes in relation to another, okay? And in particular, we're looking at how the dependent variable changes with respect to the independent variable, okay? So some very typical examples of rates might be kilometers per hour or speed in any form, the price per liter of petrol, the cost of a babysitter per hour, the population increase per year. And you can see that sort of common word in there, per, that gives us a bit of a clue that we're talking about a rate of change. We've got two variables in each of those examples, and we're looking at how one changes in relation to another. So when we have a rate of change that is not constant, okay, so that means if we were to graph the rate of change, it's not a straight line, okay, it's a different function, it's a curve. We can find what we call the average rate of change over sort of a certain interval. So for any function, y equals f of x, the average rate of change of y with respect to x over some interval a, b. So let's mark that on our graph. So say I have point A here, this would be A, and the y variable would be f at A. And let's just say I have another point B, f at B. If I want to find the average rate of change between those 2 points, okay, all I have to do is basically calculate the gradient between those 2 points, right? And the gradient of any line is just the change in y2 minus y1 over x2 minus x1. And if we take a look here, in terms of A and B, we just have f of B minus f of A over B minus A. Let's take a look at an example of how we would find the average rate of change. So in this question, we're given a function, s at t, and we want to find the value of the average rate of change of the function s over the interval 0 and then log of 8 base e. Okay, now this would come up on a calculator question, so we're going to use our calculator to do the actual calculation, but it's always handy to write down what you're going to put into your calculator in any sort of test or exam conditions. So in this case here, we want to do s at b, which in this case here is that log. So s at log 8 base e minus, and this would be our a, so minus s at a, so s at 0 over b minus a, so over, okay? And so to calculate that, we can just put that straight into our calculator to get a value. So to do this quickly and accurately in your calculator, when you have a sort of more complex function, I would suggest that you define the function first. So we're first going to define s at t. So we'll go into our menu and then our actions, and the first one is define, okay? And then we want to define s at t, so I'm just going to do s and then in brackets t equals, and then we'll put in the function that we've been given. Okay, so we'll just double check that it's exactly as it's been given in the question. So pressing enter there, once it says done, I know that the calculator has stored that function. And now I can write it in my calculator the way that I've written it on the page for you. So now I can just write s at log 8 base e. And then I'm going to subtract from that s at 0. And then on the bottom, I'll just write in log of 8 base e minus 0. Okay, and when I press enter, I get an exact value of -4 over 3 times ln 2. Ln is just log base e, so we could write our final answer in terms of log base e just to be consistent with the question. Okay, so now we're going to look at instantaneous rate of change. So the instantaneous rate of change is the rate of change at one particular point in time or one particular point along the function. And the instantaneous rate of change is just a gradient of the tangent line at that point, okay? So we can use what we've already learned about gradients and the gradient function and use calculus to calculate the instantaneous rate of change at any point, okay? So for a function, f of x, the instantaneous rate of change at x equals a is just the derivative of f at a. So because we're going to be dealing with rates of change within a particular context, you're just going to be dealing with different variables, not always y and x. So just looking at some of the examples I've included, if we just did have dy over dx, what we're talking about is the rate of change of y with respect to x. If we had something like dA, capital A by dr, this often refers to the rate of change of the area of something with respect to the radius. Or dv by dt is another commonly used example that we see. That's the rate of change of the velocity with respect to time, okay, which also refers to acceleration. Now, when we're looking at rates of change questions, unless the question specifically asks you to calculate the average, you can assume that you need to find the instantaneous rate of change, okay? So if we want to find the instantaneous rate of change of this function f of x at the point x equals 2, all we're doing is finding the derivative at x equals 2. So the derivative of f would be 4x cubed, just 4x cubed. And then at the point x equals 2, we would do f at 2, which is 4 times 2 cubed. So 4 times 8, which is 32. And in this case, we don't have any units or anything like that. We're just sort of dealing with like an abstract function. But if you were dealing with some sort of context, say, for example, speed, you might include meters per second or whatever units you're working in. So to summarize this lesson, we looked at rates of change and in particular, the difference between the average rate of change and the instantaneous rate of change. So if you have a look at the image there, that red line is giving you what the average rate of change would look like. So it's the gradient between 2 points, whereas the instantaneous rate of change at a particular point would be the same as the gradient of the tangent line at that point. So in our next lesson, we're going to move on to our next application of differentiation, which is finding the stationary points of any function. No matter how far you throw your pen, it will still be stationary. And you might have noticed when I threw that pen up in the air, it sort of pauses for a very small, slight second before coming back down. And that's what we're going to be looking at today. We're going to be looking at stationary points. So this lesson is going to focus on how we find our stationary points for any given function. So this is our third application of differentiation. It's a really, really big one. We're going to divide this lesson into, first of all, just discussing the different types of stationary points that we have, and then we're going to look at how we find our stationary points using calculus. So any point on a curve is a stationary point if the gradient at that point is equal to 0. Okay, so if a gradient, that means that the tangent line would be a horizontal line. So something like this. And remember, the gradient is just the derivative at that point. Okay, so if the derivative at a certain point is equal to 0, we have a stationary point. Okay, so there are 3 types of stationary points that we can have. We can either have what we call a maximum or a local maximum, which is, you'll be familiar with that from your work on, say, parabolas. That's one of our turning points, okay? We have minimum points, which are, like we said, like a low sort of area of the graph. Again, another type of turning point. And then we have a different kind of stationary point, which is called a point of inflection, okay? And that's where we would have, if you take a look, the tangent at one particular point would be equal to 0, or the gradient would be equal to 0, but we don't have a maximum or a minimum, okay? And those are our points of inflection. So let's take a look at each of those in a little bit more depth. So first, we're going to look at our maximum and minimum points, okay? And like I said, they're also called our turning points. And this is because the sign of the gradient changes on either side of the turning point. And what I mean by that is this, okay? If you take a look to the left of that point, you can see that the gradient of the curve on this sort of side is always positive, right? It's positive. It's getting like, not less and less positive, but it's getting closer and closer to 0 before the gradient is finally 0 at exactly that turning point. And then if we look to the right of the turning point or the maximum, you can see now that the gradient is negative. Okay, so that's what I mean by the sign of the gradient changes on either side of that turning point. And we can write this as the gradient of f, or the derivative of x, is greater than 0 to the left of the point, okay? And the gradient is less than 0, or the gradient function, sorry, is less than 0 anywhere to the right of the turning point. Similarly, but opposite, we'll look at a minimum point. You can see here, like, let's say that was my turning point right at the bottom of that curve. You can see that the gradient here is always negative on the left of the minimum, and then it's always positive on the right of the minimum point. So again, we can write this as the derivative of f is less than 0 to the left of the point, and the derivative is greater than 0 to the right of the point. Now, a point of inflection is special in that what happens is the sign of the gradient doesn't change on either side of this turning point. So let's say our point of inflection was right here at this point here. You can see if you take a look at this curve, the gradient there is positive and it continues to be positive, okay? And so we could write this as the derivative of f is greater than 0 to the left, and it's greater than 0 to the right of the point. Or we can have the opposite happening, right? In that pink curve there, you can see that the gradient is negative. We might have our point of inflection here, and the gradient is still negative. So that's how we know if we have a maximum or a minimum or a point of inflection, by inspecting what happens to the gradient on either side of the point. So does it stay positive, does it stay negative, or does it change from negative to positive or positive to negative? So our next step is we're going to actually find our stationary points. So here you want to find like the coordinates of your stationary points. So we've got some steps that we can follow here. First off, we find the derivative and then we set it equal to 0, okay? Then we'll solve for x, we'll find our y coordinate, and then we'll state the stationary point as a coordinate pair to answer the question. Let's look at a worked example and follow these steps to see how we'll find our stationary points. Okay, so this question says, find the coordinates of the stationary points of the curve with the equation y equals 2x on x squared plus 2. So my first step is I'm going to find the derivative of y, and in this case here, I'm going to have to use the quotient rule. So dy by dx, what I need first is the derivative of the numerator 2 times the denominator x squared plus 2 minus the numerator times the derivative of the denominator, which is 2x. And that's all over x squared plus 2 squared. Okay, I'm just going to leave that like that for now. So the next step here is I'm going to set my derivative equal to 0. And it's always very good to state this very clearly on your exam paper that that's what you're doing. It's often a method mark. So I'm just going to write in the statement dy by dx is equal to 0. So I want to set that whole thing equal to 0. The nice thing about a fraction is that when you set a fraction equal to 0, just the numerator has to be equal to 0 for the whole thing to be equal to 0. Okay, so it simplifies quite nicely. So what we get in the numerator there, if I expand the brackets, is 2x squared plus 4 minus 4x squared equals 0. Okay, cleaning that up a little bit, I get minus 2x squared plus 4 equals 0, and we'll just do a little bit of algebra to solve for x. Okay, so what I end up here is x is equal to either the positive or negative of root 2. So just be careful there that when you're taking the square root of a number to solve for x, that you consider both the positive and the negative square root. So that means that I've got two stationary points, one when x is equal to root 2 and one when x is equal to negative root 2. My next step is going to be finding the y coordinates for each of those x coordinates. I'm going to do that by substituting x into my original equation here. Okay, so y is equal to 2 root 2 over root 2 squared plus 2. So I'm just doing my positive root 2 value first. Okay, once I simplify that, I end up with 2 root 2 over root 2 squared is just 2, so on the bottom, I get 2 plus 2, which is 4. And simplifying that, I get root 2 on 2. So my first coordinate pair would be when x is equal to root 2, y is equal to root 2 on 2. Okay? And now I'll do the same thing when x is equal to negative root 2 to find the second coordinate pair. Okay, and that ends up simplifying to negative 2 root 2 over 4, which is negative root 2 over 4. So my second coordinate pair would be when x is equal to negative root 2, y is equal to negative root 2 over, sorry, that should be 2. Okay, I didn't simplify fully there. All right, and that's answered our question. Find the coordinates of the stationary points of the curve with this equation. So I found the derivative, I set it equal to 0, I solved for x, and then I used those x values to find the y coordinates. And finally, I've answered the question by giving both coordinates fully. Now, if you are on a calculator paper or you're able to use your calculator, a really easy way to find the coordinates of any stationary points on a curve is just to actually draw the function or draw the graph and then find them on the actual graph. So I'll show you how to do that. Okay, so we'll just go into our graphs function and we'll type in the graph that we want to graph, which is, or the function that we want to graph, 2x over x squared plus 2. And we get this here. Now you could zoom in if you wanted, like you could change this so that it's just maybe 2. And we could make this one -2, and we have a nice sort of zoomed in of the graph. And then you can see here, you can visually see a minimum and a maximum point. And so if you go into the menu and then the Analyze Graph menu, okay, and we go to, first of all, you can see number 2 there is minimum. We just need to set our upper and lower bounds like we would when we're finding any points. And you can see there that you get a minimum point at -1.41 and -0.707. And those are the sort of decimal approximations of the minimum of one of the stationary points that we found when we did this by hand. Okay, unfortunately, you will only get these as decimal approximations. Okay, we can do the same thing to find the maximum. So again, Analyze Graph and then go into maximum, number 3. Okay, and we can just highlight there the point or set our upper and lower bounds. And again, we get 1.41, which is root 2, and then 0.707, which is root 2 on 2. And that sort of verifies the stationary points that we found in the worked example. Okay, so really easy. If you have a calculator, you don't really have to do any calculus at all. You can just draw the graph and find those key points of your function visually. So to summarize this lesson, we've looked at our 3 different types of stationary points, our maximums, minimums, and points of inflection. And then what we did is we looked at how we actually find the coordinates of any stationary point. So remember, we find the derivative, we set it equal to 0, we solve for x, and then we find our y coordinates by substituting x into our original function. In the next lesson, what we're going to do is look at how we work out what type of stationary point we have. You're probably asking yourself, what do cats have to do with calculus? Well, we're going to actually come back to this in the second part of this session. Stay tuned. So in this lesson, we're going to be looking at determining the nature of stationary points. So we're going to be determining whether or not we have a maximum, a minimum, or a point of inflection. We are going to use 2 different methods to determine the nature of stationary points. So the first thing we're going to look at is called a sign diagram. The second thing we're going to do is we're going to have a look at the second derivative. So either of these can be used to determine the nature of the stationary points. You can choose the method that you like the best. So let's just take a look at a review of the types of stationary points that we have. So we can either have a local maximum, which is where we have the gradient changing from positive on the left of the stationary point to negative on the right of the stationary point. We can have a local minimum, which goes from a negative gradient to a positive gradient. Or we can have a point of inflection where the gradient either stays positive on both sides of the stationary point or stays negative on both sides of the stationary point. So in this example, we are given a function, f of x is 3x squared minus x cubed, and we're told that we have stationary points at 0, 0, and 2, 4. So in the last lesson, we looked at how we actually find those stationary points. So if you need a review of that, you can go back to that lesson. In this one, we're going to focus on determining what kind of stationary point we have. So the first method we're going to use is what we call a sign diagram, or sometimes they're referred to as a gradient table. So I've sort of set up a table here where you have 3 rows. And in the first row, you're looking at your values of x. So these are the x coordinates of your stationary points. So we were given that x is 0 and 2. And so I've just filled in those 2 x values, 0 and 2. And I've left a space before and after each of those points. Okay, now what we do is we're going to choose some x values. So we'll choose our first x value for something that is just to the left or just a little bit below 0, okay? So just pick something easy. I would just choose -1, okay, the next sort of whole number. Then what we can do is choose an x value that is between 0 and 2, so we could choose 1. And then we can choose an x value that is just a little bit bigger than 2, so we can choose the x value 3, okay? Then what we're going to do is we're going to have a look at what happens to the gradient at each of these points. Now, at our stationary points, we already know that the gradient is equal to 0, okay? But now we're going to have a look at what happens to the gradient, let's say, for example, when x is equal to -1. So the first thing I need to know is I need to know exactly what the derivative is. So for 3x squared minus x cubed, I'll just do it down here, the derivative is equal to 6x minus 3x cubed. 3x squared, okay? Now, taking x is equal to -1, let's look at what happens to the derivative when x equals -1. So I get 6 times -1 minus 3 times -1 all squared. 6 times -1 is -6. And then I get -1 squared is +1 times -3. So we have -6 minus 3, which is -9. Okay. So the gradient at x equals -1 is -9. What we're most concerned about is that a positive or a negative value? And in this case, it's a negative value. So that means at that point, f has a negative gradient. Okay, so I'm going to draw it in there. That's just giving me an idea of the shape of the graph. Okay. Now let's look at our other points. Let's look at the gradient when x is equal to 1. Okay, so the derivative at x equals 1 would be 6 times 1 minus 3 times 1 squared. So that gives me 6 minus 3, which is 3, which is a positive value. So that means that the gradient at that point is positive. Now let's look at what happens at my next point when x is equal to 3. So here I get 18 minus 27, which is -9, which again is negative. Okay, and now what I'll add in here is that when I have my stationary point 0, I've got a 0 gradient, which I can represent with a horizontal line. So here and here. Okay, so now you can sort of see here that let's take a look at my stationary point where x is equal to 0. My gradient's going from negative to positive. So from negative to positive looks like that. That means here I have a minimum stationary point. And now if I have a look at when x is equal to 2, so here, you can see that on either side of that stationary point, my gradient's going from positive to negative. So it's making this sort of shape, positive to negative. So that means at x equals 2, I have a maximum stationary point, okay? So the question says, state the nature of the stationary points. So we might answer the question by writing something like 0, 0 is a minimum, and 2, 4 is a maximum. But it's really important that we have to have proof of why each is a minimum or a maximum. So you can't just guess and have like a 50-50 shot. You need to do something like this gradient table where you're actually calculating the value of the gradient at certain points to prove whether the gradient on each side of the stationary point is negative or positive. Okay? So we can also use the second derivative to determine whether or not we have a minimum or a maximum stationary point. Okay? So the second derivative, we just calculate it by finding the derivative of the derivative. So we just do the same process twice, basically, to find the second derivative. And we have some rules here, and I'm going to explain where they come from. So if we look at this first diagram here we've got a maximum stationary point. We can see that visually. Let's take a look at what's happening to the gradient. So we know that the gradient, or the first derivative, it goes from being, so here we have a positive gradient, and then the gradient is 0, and then the gradient is negative. So the gradient is decreasing, okay? So the gradient is decreasing. Now the gradient of the gradient, that's our second derivative, Okay, so if we have a negative second derivative, okay, so if the second derivative at any point is less than 0, that means that the gradient function is decreasing. Our curve then would be a maximum stationary point, and we say that our curve at that point is concave down. Okay, so hopefully you might know that language from some of your science classes where we have something with this shape, we call it concave down. Okay, the opposite sort of happens when we have a minimum stationary point. So if we take a look, the gradient on either side of this point, so the gradient on this side is negative, and then it becomes positive. So if something goes from negative to positive in value, it's increasing, okay? So the derivative of the derivative, the second derivative, is going to be positive, okay? Because the gradient is increasing along that function, okay? So it's a little bit of an abstract concept. All you really need to remember is that if the second derivative at any point is less than 0, okay, then you have a maximum. And if the second derivative is greater than 0, you have a minimum stationary point. And a minimum stationary point, it means that the curve at that point is concave up in shape. Okay, and this is where our cute little cats come in. Okay, here we have some concave up and concave down cats. Okay, so second derivative greater than 0, we have a minimum point. That's our concave up. And then when the second derivative is less than 0, we have our concave down cat. Okay, and that's our maximum stationary point. I don't know if that's going to help you remember, but I just thought these cats were kind of a funny way to express derivatives. Okay, so let's go through a worked example to find the nature of the stationary points on a curve using the second derivative. So we've got y equals x cubed plus 3x squared minus 9x minus 1. It says find the stationary points and determine their nature. What I've done is just some working out to find the stationary points. Again, that's what we did in the lesson before this. But just to quickly recap, what we would do is we would find the derivative. We would set it equal to 0. We would solve for x. So here I got x is equal to -3 and x is equal to 1. And then we could sub those x values back into our original function to find the y coordinates. So I've got two stationary points here. Now, I'm going to use the second derivative to determine the nature of the stationary points. So the first thing I have to do is I have to find the second derivative. Okay, so our notation here is like this. Okay, so that's my second derivative. And again, I'm just going to find the derivative of the derivative. So the derivative of this would be 6x plus 6. Okay, and now I'm going to find the second derivative at my two stationary points. So when x is equal to -3, I get 6 times -3 plus 6, which is -12. Now, -12 is less than 0. Okay, so if the second derivative at a point is less than 0, then I have a maximum stationary point. Okay, so that means that the point -326 is a maximum. And then I'll do the same thing with my second stationary point. So when x is equal to 1, what happens to the sign of the second derivative? Okay, so subbing that in, I get 6 times 1 plus 6, which is +12, which is greater than 0. Okay, so if the second derivative at a point is greater than 0, I have a minimum stationary point. So I can write 1 -6 is a minimum, okay? So some people like using the second derivative test to find the nature of the stationary points because it is quite a bit quicker than setting up a whole gradient table. However, the one sort of downside of it is that if we find that the second derivative at any point is actually equal to 0, then we can't use the second derivative test, okay? And then you'd have to go back to your sign diagram. It often implies a point of inflection, but not always. We won't get into that in this course, but it does mean that you would have to then fall back on the sign diagram. So that's kind of one risk of using the second derivative test. But on your exam, either using a gradient table or using the second derivative are both ways that you can use to prove whether or not you have a maximum, minimum, or point of inflection. We can use our calculator to find the coordinates of any stationary points by just graphing the function and having a look at them visually. So let's have a look at this again. Okay, so the first thing I'm going to do is graph x minus 1 cubed plus 1. Okay, so my graph looks like this. So we've got a cubic there, and you can see visually that what you have is a point of inflection, okay, somewhere around here. So we'll just use our analyze graph function from the menu. So menu and then number 6, analyze graph. And then you can see option 5 says inflection. So that's the one we're going to try and find. And we'll just set our lower and upper bound around that point. And you can see that we have a point of inflection at 1, 1. So in summary, we've got two different ways that we can use to find the nature of our stationary points. We can either use our sign diagram or our gradient table, or we can use the second derivative test. But just remember, the second derivative test only works if we're finding maximums and minimums. If you find that your second derivative ends up being equal to 0, you are going to have to fall back on the sign diagram. Okay, so we're going to put this all together in our next lesson, and we're going to use derivatives to help us sketch graphs. So over the course of this chapter so far, we've been looking at different applications of differentiation. And in particular, the last few lessons, we've looked at our maximum and minimum values of a function. So one application of this could be a store manager that is trying to maximize their profits. However, in reality, there would be certain constraints in terms of, how many products they could order, or the price of each product becoming more or less depending on how much you buy. So these constraints, we could think of them as a restricted domain in terms of a function. So we're going to be looking at functions today that have a restricted domain where we need to seek out what is the, say, absolute maximum or minimum of that function. We are going to put all of our skills together that we know about graphs and differentiation and specific points, and we're going to use these to be able to sketch graphs today. The two key points that we're going to be covering are, we're going to look at finding our absolute maximum and absolute minimum of any function, and then we're going to take all the information that we know about the function and sketch its graph. As I mentioned in the beginning, it can be often helpful in the real world to think about what the absolute maximum and absolute minimum value of a function are. Okay, so if you have a look at the graph in front of you, you can see that there are four sort of main points that are labeled. We have what's called a local maximum and local minimum, and these are what we were finding before. These are what we found through finding our stationary points. However, if we want to find our absolute maximum and absolute minimum, we need to also consider the endpoints of the function. Okay, the absolute maximum of a function is really just where the y-coordinate is the greatest across the entire domain of the function. And the absolute minimum is where the y-coordinate is the least or the smallest across the entire domain of the function. So to find the absolute maximum and minimum, we need to take 3 steps. First, we need to find and determine the nature of any of the stationary points in that function. Then we need to work out the coordinates of the endpoints, and then we can compare all of those key points and find the greatest and least values of the y-coordinates in order to find the absolute maximum or absolute minimum. Okay, so let's work through an example to find the absolute maximum and minimum value of this function. So you can see here that we have a defined domain. So our x values are going between -2 and 2 inclusive. And our function is f at x is 2x squared plus 4x plus 6. Okay? So the first thing we're going to do is find any stationary points. And if you'll remember, we do that by finding the derivative of the function and setting it equal to 0. So the derivative of this function would be 4x plus 4. Okay, so if I set that equal to 0 and solve for x, okay, I would get 4x is equal to -4. So x is equal to -1. Okay, that's the x value of my turning point. Now I'm going to substitute x equals -1 into my original function to find the y-coordinate of that point. Okay, so working that out, I get 2 minus 4 plus 6, which is 4. So that means I have a stationary point, at -1, 4, and we'll just highlight that. Okay, the next thing you might want to do is determine the nature of that stationary point. Now for this function, you should be able to recognize that you have a parabola that's opening up, so this should be a minimum point. But let's use our sign diagram just to practice that method to verify that we've got a minimum at -1, 4. So I've just set up my sign diagram or my gradient table, and I'm going to have a look at what is happening to the gradient of the function just to the left of -1 and to the right. Okay, so if I take a number that is just to the left of -1, that could be -2. And if I substitute that into my derivative, I get 4 times -2 plus 4. And that's going to be a negative value, okay? So the shape of the function is going to have a negative gradient at that point. At -1, we know the gradient is 0 because that's our stationary point. And now we'll take a value to the right of -1. So let's say x is equal to 0, and I'm going to sub that into my derivative. So I get 4 times 0 plus 4, which is a positive value. Okay, so I get something like this. So you can see from this diagram that I do in fact have a minimum value at 0 because the gradient goes from negative to positive along the graph. Okay, the next thing we need to do is work out the coordinates of our endpoints. Okay, so first I'll take a look at when x is equal to -2. So I'm going to substitute that directly into f of x. Here I end up getting 2 times 4 is 8, minus 8 plus 6. So one of the coordinates of my endpoint is -2, 6. And then I'll find my other endpoint, which is when x is equal to 2. Okay, so here I end up with 2 squared is 4, times 2 is 8, plus 8 plus 6. So we end up with the value 22. So that means my other endpoint is at 222. Okay, and now I'm going to take a look at these 3 points. So I'll just highlight the other 2. Okay, so taking a look there, my greatest y value is 22. Okay, so that means I have an absolute maximum at the point 222. Okay, and then taking a look at my y values again, I'm going to look for the smallest y value, which is 4. So that means I have an absolute minimum at the point -1, 4. Okay, and if we thought about the shape of this graph, which we should sort of always do, is we would have something like this, where my first endpoint would be at -2, 6. Here's my stationary point at -1, 4. And then here's my maximum, my absolute max at 222. Okay, and that's sort of the shape of the graph, so you can see clearly there where your absolute maximum and minimum values are. So for the second half of this lesson, we're going to take everything that we've learned about key features of functions, and we're going to put them all together to sketch graphs. Now, if you have to sketch a graph on a tech-free paper, normally you'll be told which features or which key points you need to include on your sketch. So read the question very, very carefully. But typically what you'll want to be able to do is find the x and y intercepts of any graph, find the stationary points, find any endpoints, and then make sure you know the correct shape of your function. Okay, so we're going to go through a whole worked example to see how we could put everything together. So we've been given a function, we've got a restricted domain, and we want to sketch this graph. Okay, so the first step is we're going to find the coordinates and the nature of any of our stationary points. We've done this quite a few times over a number of videos, so I'm going to go through this one a bit more quickly for you. Okay, first thing is find the derivative, set it equal to 0, and solve for x. Once I know my x coordinates, I can substitute them back into the original function to find the y coordinates. Okay, so here I've got 2 stationary points at 0, 0, and at 1, 2. I'm going to now work out whether we have maximums or minimums or points of inflection. So I've set up my sign diagram. I'm now going to choose points that are just to the left and right of my stationary points. So just to the left of 0 would be x is equal to -1. So I want to find out what's happening to the derivative when x is equal to -1. So if I sub that into my derivative, I end up with -12 minus 12, which is -24. So I've got a negative value there. So my graph is going to be decreasing at that point. Okay. At 0, we know the gradient is 0, so I've got just a horizontal gradient there. And now I've got to pick a point between 0 and 1, so I'll just pick a half. So if I substitute x is equal to a half in there, I get 6 minus 12 times a quarter. So that ends up being 6 minus 3, which is 3. Okay, so here I've got a positive gradient, or the graph is increasing in that section. At x equals 1, I know the gradient is 0. And now let's pick a point that is just a bit bigger than 1, so x is equal to 2. And here I would have 24 minus 48. So that's going to give me minus 24. And again, the graph is negative at that point. So you can sort of see the shape of the curve. I'm going to start to mark these in on my sketch. Okay, so part B is sketching the graph, labeling my axial intercepts, endpoints, and stationary points. So I already have the stationary points. One of them is at 0, 0, and we've just got a sketch here, so we'll just estimate. So I've got x is 1, y equals 2, somewhere up here, okay? And I know the graph's going to go something like, so it was negative to positive to negative, something like that. So now let's mark in my axial intercepts. Well, I already know one x and y intercept is at 0, 0. I can tell from the shape of this graph that I need just one more x-intercept. So to find the x-intercept, I need to set y equals to 0. Okay, and solve for x. So here I get... So I'm going to get x is equal to 0, which we already knew. Or for this other one, I'll end up getting what is 3 minus 2x equals 0. So 2x is equal to 3, so x is going to be 3 over 2, so 1.5. So this other x-intercept is going to be the point 3 over 2, 0. Okay, and there's my axis-intercepts. I don't need to find the y-intercept because I've already found it. I can tell by the shape of the graph that's the only y-intercept. Okay, the last thing I need are my endpoints. All right, so let's take a look at the domain. Okay, my lower endpoint is at -1, so let's find out the y-coordinate of that endpoint. So f at -1. Okay, so my first endpoint is at -1, 10. So that would be this point here, -1, 10. And that's good. That sort of confirms the shape of the graph for me. That point looks like it's in the right place. And let's find our other endpoint. So that's when x is equal to 2. So if we do f at 2, we get 6 times 2 squared minus 4 times 2 cubed. So working that out, we have 24 minus 32, which is -8. Okay, so my second endpoint would be the point 2, -8, which is down here, to -8. Okay, and there's my graph. Now looking at this, we can also sort of ascertain what is my absolute maximum and my absolute minimum. Okay, so you can see that my absolute maximum would be that endpoint there, -1, 10. That's where my y value is the greatest. And you can see my scale's not actually very good here because that point is just 1, 2. So it should be like a little bit lower maybe when I sketch it, but that's okay as long as it's labeled properly. And then my absolute minimum would be this point here, that endpoint when x equals 2, y equals -8. My stationary points that I found, those will be what we refer to as our local maximum, and this one here would be my local minimum. Okay, so they are minimums and maximums in those like sort of little local areas of the function, but the overall absolute maximum is the left-hand endpoint, and the absolute minimum would be that right-hand endpoint. Okay, so to summarize this lesson, we first looked at what is the difference between the absolute maximum and minimum of a function as opposed to just a local maximum or a local minimum. And we had some steps to work out what are the absolute maximum and minimum. So we needed to find any stationary points, work out the nature of those stationary points. We needed to find the value of any endpoints, and then we need to see where is our biggest or greatest y coordinate and our smallest y coordinate across the domain of the function. Okay, and when you're sketching a graph, there are some key features that you may need to include on the graph. So you need to be able to make sure you know how to work out the x and y intercepts, the stationary points, any endpoints, and you need to be familiar with the correct shape of all of the functions that are included in the methods course. Okay, coming up next, we're going to take all of the work that we've been doing with differentiation and we're going to put this into context. So we're going to look at some real life examples of applications of differentiations and in particular, looking at what we call optimization problems. So you may have been drinking a refreshing beverage and thought to yourself, why is this can shaped the way it is? Well, there's lots of reasons that manufacturers will shape different products the way that they are. But a big part of that will be them looking at how to try and minimize the amount of material that they're using to create their product. And that's where some calculus can come into play. Now, if you're interested in finding out a bit more about why the Coke can is shaped the way that it is, I have linked to a video where you can investigate a little bit further. It's quite interesting, not quite needed for the maths for this course, but we are going to be looking at what we call optimization problems in this lesson, which is where we might have to maximize or minimize a certain quantity. And this is a huge application in any sort of like business or economics. So this lesson is going to be looking at our applications of differentiation and in particular our optimization problems. So we've split this lesson into two sections. In the first section, we're just going to look at reading through a problem and setting up the equation that is going to help us to optimize a certain variable. And then in the second section, we're going to go ahead and solve the problem using calculus. So far when you've been studying calculus, you might have been thinking, like, is this really useful in any way, shape, or form? And the answer is a definite yes, okay? So differential calculus is used to solve a lot of real-life problems where a quantity needs to be either maximized or minimized. So I've listed a couple of examples there for you. For example, what's the quickest way to get passengers on a plane? What's the optimal price of a product that will maximize its profits? When you're drinking coffee, what's the peak concentration of caffeine in the blood and what time will that be, etc., etc. There's like an infinite amount of applications of these types of problems. Now, in terms of your questions that you need for your methods course, there are some pretty standard types of problems that you do see come up again and again on the exam question. So I've tried to focus on these types of problems in this lesson and also in the topic test for this chapter. So I've got for you here a pretty comprehensive list of steps that you can go through to solve optimization problems. Now, each problem is not going to need every single one of these steps, but I'm going to take you through a couple of different types of problems so you can see what each of these steps look like. The first three steps really have to do with setting up your equation. So often you're not given an equation in these types of problems. You have to make up the equation yourself. And that can often be the most complex part of these optimization problems. So that's why we're going to spend the first section of this lesson going through just that stage. Now, we often want to draw a diagram if it's applicable. First of all, so we can get a visual sense of our problem. And then we're going to write an equation for the variable that is to be optimized. So that will be told to you in the question. You'll be asked to maximize or minimize something. And then you may need to find a connection between more than one variable. So we'll have a look at that type of problem when we do our worked examples. Now, one thing that can really trip students up in this type of problem is they understand the calculus behind it, but it's actually some of the basic algebra that we need to remember in order to solve these problems. So don't forget how to rearrange equations. That's a big key skill for this type of problem. Let's look at our first worked example. A standard can of Coke in the shape of a cylinder is 355 milliliters. What are the dimensions of a can of Coke that would use the least amount of aluminum? First step is to find an equation for the surface area of the can in terms of the radius. Now, let's take a look at the information we're given in this question. First of all, we're told we're using the shape of a cylinder. So I'm going to sketch myself a little cylinder here. Okay. Now, I would start by labeling the key sort of variables in the shape that you're given. So in a cylinder, we often need to know the height, or we need to know the height, and we need the radius. Those are the two variables involved with the shape of a cylinder. Now, we're told it's 355 milliliters. Okay, that is the volume. So I'm just going to write down that the volume is 355, and we'll just leave the units off for now, milliliters. Okay, now, if we want to use the least amount of aluminum, though, we're actually talking about surface area, okay? So we need to think about the surface area of the can. That's what we want to be minimized, okay? So that's the formula we need to come up with. Okay, so this is sort of going into step 2. We don't know the radius or the height of the cylinder, so I'm just going to leave my drawing as is. But step 2 says write an equation for the variable that is to be optimized. Okay. So what I want to be optimized here is the surface area. The surface area of a cylinder, okay, is going to be 2 area of a circle, so 2 pi r squared, okay, plus that curved surface area there, which is the circumference times the height, 2 pi r h. Okay, and now this says if more than one variable is used, so this is in step 2, if more than one variable is used in the question, find a connection between the variables. Okay, more than one variable is used in this question. We have radius and we have height. Okay, so what we need to do is we need to use the other piece of information we've been given, the volume, to find a sort of a connection between these variables. So volume, I know, is pi r squared h, okay, volume of a cylinder. So I can write 355 is equal to pi r squared times h. Now in the question, I want to write the equation for the surface area in terms of the radius. So I want an equation for surface area that just has the variable r in it. So what I need to do is I need to find h in terms of r, and I can do this using my volume formula. So if I rearrange this, I could divide both sides by pi r squared. So 355 divided by pi r squared, that's equal to h. And so what I can do is I can substitute h into my surface area formula to find my equation just in terms of one variable. Okay, so I'll do that in step 3 here. I get 2 pi r squared plus 2 pi r. Now instead of h, I'm going to substitute h is equal to 355 over pi r squared. So I'm just going to simplify that equation a little bit. You can see here in the second term, my pi's will cancel out, as will one of the r's. Okay, so what I'm left with is surface area is equal to 2 pi r squared plus 2 times 355, which is 710 over r. And now I've got an equation for the surface area, which is what I want to minimize in terms of just one variable, the radius. And that's the first step, okay? So you can see that that takes a little bit of work, making the connections between what you want to optimize, the information that you've been given, the formulas that you know about different shapes to come out with this final equation here, okay? So we're just going to stop that there for this question. We're going to go on and solve it in the second part of this lesson. Okay, let's take a look at a different type of optimization problem here. The cost of a flight from Melbourne to Brisbane is $500. The capacity of this plane is 300 seats. So on average, 180 seats are sold on each flight. Market research has shown that for every $5 reduction in the cost of the flight, 3 more seats are sold. So how much should the airline charge for the flights in order to maximize their revenue? Okay, so in order to work this out, we first need to find an equation for the revenue in terms of the number of $5 reductions. All right, let's sort of take this apart a little bit here. We've got a question here that is talking about maximizing revenue. So we want a formula for revenue, okay? And very simply, the revenue of anything is going to be the number of units sold. So I'll just write this out. The number of units sold times the price per unit, right? So the airline, if they say sold all 300 seats for $500, their revenue would be 300 times 500, okay? Very simply. Now, what we have to ask ourselves here is, what is impacting the revenue, okay? And so what variable do we need to look at that is impacting the revenue? And what is impacting the revenue is how many like $5 reductions we have. So we're going to define a variable here. We're going to let n represent the number of $5 reductions. Okay, so let's try and put together a formula for the revenue. Now, the number of units sold. So on average, we have 180 seats sold, right? Okay, but if we have, say, one $5 reduction, we're going to sell 3 more seats. Okay, so the number of seats sold is going to be 3 times the number of $5 reductions. Now, the price of each flight starts at $500, and we're going to subtract $5 every time we have a reduction, okay? So it's going to be 500 minus 5n. So here we have an equation where we only have one variable. There's not really a diagram to draw, but it's a little bit tricky to think about how we come to that equation. So we actually, all 3 of those steps I've just put into one here, because in this one, we just need to write an equation for the variable that is to be optimized, okay? We don't have any more variables. We just have the revenue being optimized and then the number of $5 reductions. And here we've written our equation for this type of problem. So we're going to stop there for that one. In the second section, we'll go through the calculus that is needed to actually solve this problem. Okay, so now that we've got through the hard part, which is setting up our equations, we're now going to use calculus to find the solution to our equation. So step 4 is key here. Whenever you see a question that's asking you to maximize or minimize something, you're going to have to use the derivative. Okay, exactly what we've been doing in our other lessons to find our stationary points. You need to differentiate your equation, set it equal to 0, and solve for the unknown variable. Now, step 5, 6, and 7 don't apply to every single question. You'll only do those things if necessary. You may need to reject any unrealistic solutions. So that might be if you're talking about dimensions, and you get a negative and a positive answer, you would only include the positive answer because you can't have a negative length, for example. You might need to check the nature of your stationary points. So you might need to check if you have a maximum or a minimum, but often that information is given to you in the question anyway, okay? If you have a restricted domain, you might need to evaluate your endpoints and check for any absolute maximums or minimums. And then step 8 is also very, very, very key. You want to go back and reread the question and make sure you've answered what the question is actually asking you. Okay, let's take a look at our examples that we've been working on in the previous section. Okay, so back to our can of Coke example, we wanted to find, so the question is, what are the dimensions of a can of Coke or a Coke can that would use the least amount of aluminum, okay? And the connection you have to make there is when we're talking about the least amount of material for something, we're often talking about the surface area. So we want to minimize the surface area. So from our previous work, we had an equation for the surface area. We also had an equation for the height in terms of R. Okay, so we might need to use those. All right, my first step is I'm going to differentiate my surface area formula. Okay, so I'm going to label this as ds by dr, okay, because I'm doing the derivative of the surface area with respect to the radius. So 2 pi r squared, the derivative of that would be 4 pi r. And then 710 over r, we could write that as 710 r to the negative 1 in order to be able to differentiate. So that's going to become negative 710 r to the power of negative 2, or over r squared. Okay, so that's the derivative of my surface area. And now I want to set that equal to 0 and solve for r. So for this question here, in order to solve for r, I would first multiply everything by r squared to get rid of that fraction. So I end up with 4 pi r cubed minus 710 is equal to 0. I'm going to add 710 to both sides. I'm going to divide both sides by 4 pi. And then I'm going to find the value of r by taking the cubed root of 710 over 4 pi. Now, obviously, something like this, if you were expected to answer as an exact value, you would leave your radius like this. Often, within a context, you might be asked to round to 2 decimal places. So you can just pop that into your calculator, and you end up with 3.84 centimeters, correct to 2 decimal places. Now, we don't have to check the nature of the stationary point because we've only got one value for r, and we've already told that we're trying to use the least amount, so that is a minimum value. So we don't need to reject any unrealistic solutions because there's only one solution here, and it does make sense, right? 3.84 centimeters for the radius of a Coke can seems like a value that would fit. Okay, we don't need to do this because we've been told we're looking for a minimum, and we don't have any endpoints in this case to evaluate. So really, we just need to go back to number 8 and make sure you've answered the question. Now, the question asks me for the dimensions of a Coke can. So the dimensions would be both the radius and the height. So the next thing I need to do is just go ahead and work out the height. So I can do that by just subbing r. And I would use your exact value because for this kind of thing, you'll have your calculator. So I would sub this value here into my equation for h. Okay, so you're going to substitute that in. You can do all that work using your calculator really easily, and you end up with h is equal to 7.67 centimeters for the height. Okay, so we've answered the question. We might run because it's a word problem, we can write the dimensions that would use the least amount of aluminum are a radius of 3.84 centimeters and a height of 7.67 centimeters. Okay, let's go on to our next example. So now we're looking back at our flight example. And if we recall, we had our formula for revenue, which was 500 minus 5n times 180 plus 3n. If you expand those brackets, we end up with 90,000 plus 600n minus 15n squared. Now, we do have a restricted domain in this question because of the context of the question and the restraints within the number of seats that we can actually sell. So if we take a look, the lower bound of the domain would just be 0. And that's if we have no reductions in flight, okay? So that would be if we just stayed with our price being $500 and we sold 180 seats. Now, the maximum value for n is 40. And this is because we can only sell a maximum of 300 seats, right? It says that the capacity of the plane is 300 seats. So if we do 180, that's our average, plus that 3n for every reduction, the maximum amount of $5 reductions we could have would be 40, because that would give us 180 plus 3 times 40, which is 300. So if you'll recall, we had this equation for our revenue. And if you expand those brackets, you end up with r is equal to 90,000 plus 600n minus 15n squared. We do have endpoints here, okay? Because what we're thinking about here is how many reductions could they actually have realistically. Now, you could have 0 reductions, right? You could keep your flight cost at 500. But if we're talking about $5 reductions, the maximum amount of reductions we could have is 40, which is probably a bit unrealistic, but that would make the flight $0. Okay, so those are the domain for this problem here. Okay, so we've got our formula here and we want to maximize the revenue. So what we're going to do is we're going to find the derivative of our formula for revenue. Okay, so our revenue is Rn, so I'll just rewrite that. Okay, and now let's find the derivative of r with respect to n. So that's going to be 600 minus 30n. Now we'll set that equal to 0 and solve for n. So solving for n, I get here that n is equal to 20, okay? So what does this mean in terms of the context of this question? Well, what it means is it's telling us that we should charge for the flight. So the question is, how much should the airline charge? So they should charge $500 minus 5 times 20. Okay, so they should reduce the price of the tickets to $400 in order to maximize their revenue. Okay, let's just take a look again. Let's just like sort of unpack this question a little bit more. And let's check what the revenue actually is. And we can compare that to the endpoints. So we're kind of looking for our absolute maximum value here, making sure that this is our absolute maximum. So the revenue, if we did 20 price reductions, would be, we're now charging $400 for each flight. And how many flights are we going to sell? Well, we're going to sell our 180 plus 3 times n, okay? So 180 plus 60, which would be 240. So the revenue here would be 96,000. Now, if we didn't do any price reductions, okay, so that's the revenue if we did 20 price reductions, $25 price reductions. Let's look at the revenue if we did 0 price reductions. Well, that would just be our initial scenario where we were selling 180 flights for $500. So our revenue now would only be $90,000. Now let's check what would happen is if we did n is equal to 40. So if n is equal to 40, that's my other endpoint. Okay, I would do, my cost would be 500 minus 5 times n. So 5 times 40, which is 200. So the cost would be 300. But that's actually selling my maximum amount of seats. Okay, so 180 plus 3n would be selling 300 seats. Okay, so 500 minus 200 is 300. Again, we get a revenue of $90,000. Okay, and that's if I sold the most amount of seats that I could. Okay, so we can see here that where we had the revenue where we were doing n is equal to 20, that does give us our maximum revenue. So right, for this type of question, we were looking at the endpoints of our domain to make sure that the stationary point that we found was the maximum. Okay, so let's go back and reread the question. It said, how much should the airline charge in order to maximize their revenue? Well, they should charge $400 to maximize their revenue. Okay, so that gave you a couple of examples of optimization problems. There's a couple more for you to try in the Chapter 8 chapter checks, but just a summary there for you of your steps. First of all, you need to do some work to set up your equation, and then you'll go through and solve the problem, thinking about the actual context of your problem when doing so to make sure that you follow the steps that you need to. And again, don't forget to reread and make sure that you've answered the question. So the next thing that you need to do is just go through all of Chapter 8 and attempt those chapter checks.